Okay, so here we go now to 8.3 for the second lecture. We just saw on this slide how your pKa plus pKb will add up to be 14, as illustrated by this combination of the two forms of a chemical reaction. So let's take a look at this right now. If you know the pKb value associated with it was found to be 15.5, you know that to figure out the pKa, you have to add those numbers up to get 14. So what number do you have to add up to get 14? For pKa, a negative 1.5 will give you 14 for that. So you can see that our pKa value very small, making that an acidic solution. Okay, as we mentioned, it's kind of like pH. When it's small, it's going to be on the acidic end. Now, this one we're just going to kind of answer for you. Is the conjugate base a stronger or weaker base than that of water? And the answer is the conjugate base is weaker than that of water because water will always compete for protons, and it wins every time because it makes such a strong acid as the conjugate acid of that, of course, H3O+, and we said it doesn't get any stronger than that. So in a case like this, to answer that question, the conjugate base will be weaker than that of water. Okay, so find the pH of a 2.5 molar solution of hydrogen fluoride. So the first question we need to ask is that a strong acid? A lot of people forget and think that is one because all the other halogens make up strong acids, but this is the exception. So the answer is no, so it's not 2.5 molar H. You don't know what that is. So what we have to do is figure that out using the Ka of this equilibrium system, which we're not sure which way it slides. We're guessing it's going to be pretty strong in this direction because it's a weak acid. And this does give us some hints that the pKa is 3.14. So we need to get that as a Ka because that's the true equilibrium constant. And remember, all you do is raise that to the negative power of the pKa, as we did here, 10 to the negative 3.14, and Ka value is 7.2. Remember, this is 2 sig figs, and that's 2 sig figs as well. So, fits right in that wheelhouse of being a weak acid, not super weak. That's not a super small number, but it is small. And now we have to find the H3O+ by using the ice box. Okay, so remember, initial change, which also stands for coefficients, which in this case it's all 1 to 1 to 1, and then your equilibrium concentration. So we do know that it was 2.5, and this was a strong acid. This would be 2.5, and that would be 2.5, and it would be done. But it's a weak acid, so we have to look at the change, and we don't know what that is. So that's minus X from the reactant side, and plus X for each of these two reactants. And then you just fill in the rest, and you set up your equilibrium constant, which just happens to be Ka. Put the products on the top, the reactants on the bottom, and say that's going to equal 7.2 times 10 to the minus 4. So that's why we had to figure this out So we could plug this in and solve this. Now, you could be staring at some pretty tricky math, but this is a weak acid, so we know that X, these guys, are going to be very small as products. So compared to this, if you're subtracting it, it's not going to affect it. It'll still be 2.5. So you can just leave that on the bottom. So now you go ahead and take x squared, of course, is going to be bring this 2.5 over there. You're multiplying those together and taking the square root, and you're watching your sig figs, which of course 2 all over the place, 2. So boom, answer 0.042 molar. All right, and both of those two things will be equal. So not even close to the 2.5 molar that you would have incorrectly guessed if you thought it was a strong acid. So we're not done yet, but you do have the hydrogen ion concentration, and if you can plug that in to the negative log of the H plus or H3O plus, and remember that's 2 sig figs, and so is this one. 2 places to the right, pH is 1.38. So yeah, it makes a pretty low pH. It's not a super wimpy acid, but certainly does not meet the definition of being a strong acid, because it made very small amount of product here, only 0.04 molar. Okay, so we'll continue this by looking at something called percent ionization. So here we have hydrogen cyanide, which you remember from the previous lecture is a very weak acid. So you wouldn't expect this to happen very much at all. And such a weak acid, you would predict a higher pKa value, just like we had talked about with pH and pOH and so on. So super weak acid. All right, so let's find out what Ka is, and we're going to get the pH and the percent ionization. So a couple different steps here. All right, so to find Ka, remember you just raise it to the negative power of the pKa, and then you can see that'll be 2 sig figs. So as predicted, a really small Ka, because we had a relatively big pKa, so super weak acid as predicted. So that is a start. We now have Ka, and then it's time to go to the ice chart again. And knowing that we started off with 1.5, 0 and 0, minus x plus s plus x, and very similar to the previous problem. As a matter of fact, if you want to do the next step here, try the math and see what you get before you should be able to even set this all up on your own right now. And you solve for x using the same reasoning that we did on the previous problem. So hit the pause, give it a try. Boom. You get to assume that x is not going to affect 1.5 minus it, because it's going to be really small. You're going to solve for x, and you get 2.7 times 10 to the minus 5th molar. All right? So very low concentration of your product, but that will allow you to find the pH, because you can just plug that in. Whoopsie daisy. There we go. You can plug that right into that equation right there. Negative log of the hydronium ion, and then just put that number in there, and you end up with 4.57, which of course has 2 sig figs for a pH value. Okay, so super weak acid, but still, can change the pH significantly of a system. Okay, that shows you how delicate that pH scale is. And now for the finding the percent ionization. Okay, how do we do percent ionization? Well, let's start off by defining what this means. Remember how we talked about the HA, HA, your initial over the ion that is formed from the acid. So in this particular example, you got lots of HCN, and then a few of the CNs break off a little bit, and then we can talk about the percent of ionization. So we know that the initial concentration was this, and the wimpy little cyanide concentration was that. Divide them out, watch your sig figs, you get a percent of 0.0018. Remember, you are multiplying by 100 because of the percents when you're doing these problems. Okay, and we'll actually start our next lecture with this problem, just because we're going to try and kind of break it in half. I am going to post all the answers for 8.3 and setups, so you can start working on the problems and get through as many until you start kind of not understanding them, because we have to finish the lecture for our Wednesday class, and we'll be doing that on Wednesday. Okay, so this will give you plenty to do to get started on those, and of course finish the 8.1 assignment, which is due right away tomorrow morning. Okay, take care.